In addition to a changing magnetic flux through a closed loop of wire, causing an EMF, there's another way we can get an EMF induced in a conductor. It doesn't have to be a loop of wire, just a piece of metal. A conductor, moving in a magnetic field, may experience an EMF across the conductor. Let's take a look at that. It's called motional EMF. Here I have a thin rectangular conductor sitting in a magnetic field that points into the page. Let's get this conductor moving to the right at some constant velocity. Conductors are full of electrons that are free to move. The first electron that moves is going to feel a force. It's moving to the right in a magnetic field that points into the page, and it's a negative charge, so it feels a force toward the bottom of the page. It's going to end up at the part of our conductor closer to the bottom of the page, and it's going to leave a proton behind. And the second electron that moves feels a force because of its interaction with the magnetic field that points toward the bottom of the page. But there's an electron already at the lower end of our conductive material that repels it, and a proton towards the top of the page in our conductive material that attracts it. So there's an electric force that points in the opposite direction. Well, at first, the electric force is not going to be as strong as the magnetic force. The electrons will keep moving down and building up down here, leaving positives behind. And eventually, the electric force will get bigger and bigger and bigger until it equals the magnetic force. And then the charges stop moving. No more electrons move because the force on the electron causing it to move towards the bottom of the page due to its interaction with the magnetic field is equal to the force on the electron causing it to go towards the top of the page due to its interaction with the other electrons that have already moved. So let's see, when do those two forces equal each other? Our conductor is in a steady state after a certain amount of time passes, and the electric force and the magnetic force are equal and opposite. No more charges are moving, and our conductor is just moving through the magnetic field at a constant velocity. So we fill in what we know about charged particles moving in magnetic fields, and we fill in what we know about charged particles in electric fields, and we end up with the electric field is equal to the velocity times the magnetic field. Now let's try to figure out what the electric field is in terms of the dimensions of our conductor. We know that the change in potential, delta V, across some region of space is equal to negative E times the distance if our electric field is constant. We don't care about the negative sign here. We just want to know what the potential difference is across our conductor. So I'm trying to be careful here. This capital V is electric potential difference. And this little lowercase v is velocity. So I'm just going to take the absolute value of both sides. Our potential difference is just the electric field multiplied by the distance. And what is the distance? The charges are building up at the lower end and at the upper end of our conductor. So the distance is L. We'll just call it the length of the conductor, L. So solving for the electric field, the potential difference divided by the length. Now we can plug that back in over here, and we get the potential difference over the length is the velocity times the magnetic field, or the potential difference is BLV. And one more time, this little v is velocity, and this capital V is potential difference. Let's take a closer look at Faraday's law and induced EMF. Faraday's law tells us the induced EMF in a region of space is equal to the change in flux with respect to time, multiplied by the number of turns. This is true for any region of space, whether we have a loop of wire there or not. If we have a region of space with a changing magnetic flux, we can say there's an EMF induced in that region of space. If there's a path for the electrons to move, like a wire loop, then we get a current also. But if there's no path for the electrons to move, we would still have an EMF induced in that region of space. Flux, we know, is the integral of B dot dA. What could cause the flux to change? The magnetic field. And that's the example we did in the previous video. Moving a magnet closer to a loop of wire is, in essence, increasing the strength of the magnetic field at the location of the loop of wire. Moving it farther away is decreasing the strength. So by changing the strength of the magnetic field, that's one knob we have for changing the magnetic flux. What else would affect the magnetic flux? The area. Changing the size of our loop of wire, changing the area of our loop, will also change the flux. If we all of a sudden make our loop bigger, we get more flux. Even if the magnetic field stays exactly the same, everything's exactly the same, we make our loop bigger, there's more flux going through that loop now. So changing the area is another knob we have for controlling the flux. And what's the third knob? What else can we do to control the flux? We can change the orientation between B and dA. If our magnetic field lines point in one direction, and we take our loop of wire and we rotate it so it's perpendicular to those field lines, and then we turn it so it's parallel to the field lines, we've drastically changed the flux through our loop of wire. So we can change the magnetic field strength, we can change the size, right, the area of our loop, and we can change the orientation between the two of them. Any one of those will change the flux, and as long as the flux is changing, we can have an induced EMF in our loop. Let's look at an example where the area is changing. One way to change the area is to put together some conductive rails and have another conductor that rests on top of those rails and can slide back and forth. So we can slide this conductor back and forth on our conductive rails. If we move it to the right with some constant velocity, what's going to happen? We're going to change the area, and that's going to change the magnetic flux through the loop. So the magnetic flux through the loop is into the page, and it's getting bigger and bigger as the area gets bigger and bigger. So a current is going to get set up. That changing magnetic flux is going to cause an EMF in the loop. It's going to cause a current to flow in the loop that creates its own magnetic field that opposes this change. So it wants to get it back to a small flux into the page. It starts out, there's a small flux into the page, and as the area gets bigger and bigger and bigger, the flux increases and increases. So it wants to reduce it back down to its starting value. So it has to create a magnetic field that points out of the page. So we're going to get a counterclockwise current flowing when this conductive bar slides to the right on those rails.